Okay, so you're looking at cos, and you've discovered that cos starts at a bit of a different spot. So we're going to actually go take a look at the graph here. I will turn off the sine graph, and I'll turn off what we have written here. So clear it, and we'll turn off sine. And you'll notice that cos is a little bit different, right? Where sine starts, or if you were to call this a starting point, because technically they're infinite, they go on forever. If we want to give it a starting point, it's at 0, 0, where cos actually starts at 0 and 1. They both follow the same pattern. They have the same high points and same low points, you'll notice, but the x values, or when they get there, are a little different between the two. Now, with sine, when we punched it in, we were getting, the program here was kind of giving us very long decimals, not technically exact values, but somewhat of an approximation, and we were rounding it even more. But we can get far more exact than what the computer was getting us in terms of an answer. So let's turn these two off. You'll notice here are our key points again. I'll just quickly highlight them. And then what we'll do is we're going to jump back and then fill in the other parts. So what's neat about cos is I'm going to ignore this one at the moment. I'll just quickly erase it actually. We go to 1, and then at pi over 2, which for sine you actually get to 1 again, this is actually 0. And when we get to pi, we're actually at -1. We'll go back up to 0 when we get to 3 pi over 2. And then finally at 2 pi, we're at 1 again. It does a full rotation. And where sine, we kind of, looks like we start in the middle, go up, down, and then back to the middle. If that's the general understanding of sine, you can technically start anywhere. For cos, and I'm writing x, but you could technically write it as theta. Cos is seen a little more like if you were to start at 0, it goes from the top down to the bottom, back to the top again. Okay, and it's following all these major points. So what we can do is when we relate this to our special triangles to find exact values, instead of punching it into the calculator like we had done over here, and it gave us like an approximate decimal that looks like it goes on forever, but we couldn't write it all in. We recalled that this was 30 degrees, 45 degrees, and 60 degrees, okay? If we use cos, and we could have used sine before, we can create these triangles. This is what we did the other day. We have 30 degrees, and we have 60 degrees. Remember that this kind of triangle is a 1, 2, 3 triangle, they call it. So 1, 2, and then root 3, okay? And if I'm at 30 degrees or pi over 6, and remember this one's technically pi over 3, this is actually pi over 2 in terms of the angles. If we're at pi over 6 and we're looking for cos, cos is adjacent over hypotenuse. Well, the adjacent is root 3 over 2. An approximate value, you could kind of jump back to the graph here, and you could say your approximate value for your 30 degrees or pi over 6. Let's see if we can quickly do it here. We'll give an approximation. Y equals cos x, but this time I'll turn it into a table, and we'll change it to black so that it matches what we had before. If we type in pi over 6, okay, we get that same value we did for cos. So we'll actually do the exact same stuff we had done before. This one ended up being pi over 4. And we get pi over 3 as another one. Divided by 3 is another value I believe they have in there, okay? These are the exact same values, but what we're going to do is we're going to use a special triangle to kind of solve them. So we'll say that this one was 0.9-ish approximately, okay? Pi over 4 is actually our 45 degrees, right? Pi over 4. So our isosceles triangle we'd worked with before. But again, remember, we're using cos. So cos is adjacent, and in this triangle, we have a 1, 1, root 2, okay, as the measurements. Well, adjacent over hypotenuse would give you 1 over root 2 as a value. That ends up being approximately 0.7-ish, they say. And then finally, pi over 3, adjacent over hypotenuse. Well, adjacent is 1, hypotenuse is 2. That is 1 over 2. The approximation is 0.5. So we can actually jump back to our previous page here, And though we had these values like this, we're writing in the decimal, we can use our special triangle again to figure them out. This was essentially a half if we were to use our special triangle. This one ended up being, let's see what 0.7 is. 0.7. Did I write it out? Oh, sorry, I'm in the wrong page here. If we jumped over. 0.7 was 1 over root 2. Let's go back. So this one actually ends up being 1 over root 2. And this one ends up being your root 3 over 2, which would be your more exact values. So we can use those concepts to kind of jump through the page. And remember, because this is on its way down, this is actually when we hit 0. Those same values are just on their negative end here. So this is, we can kind of go around our Cartesian plane, and we can use these exact values once again to figure out where it is we're going. We just reverse them in the same order. In this one, we end up with negative a half. This one being negative 1 over root 2. And this one being negative root 3 over 2. And then we could use these same approximations just in their negatives. Negative 0.7 and negative 0.9. And then because we've got to the bottom, we go on our way back up to the top. So we take these values and actually put them in below. It ends up being the same concept when looking for exact values. Oops.